That is our, what operation? I know. Characteristic operation for algorithms, right? So how many times, so let's say we go into the outer loop and the value of I is equal to 0. Then the inner loop goes from 1 to 1 to less than n to the 0. I guess it's 0. Right? Because it changes all the time, right? Based upon I. So the first time when I is 0, it goes from 1 to n to the 0. N to the 0 is 1, 1 less than 1. Now, if I can make it a little bit simpler, not really a lot. If I make it equal here, less than or equal to, then it goes from 1 to 1.
Yeah.
So it's going to do one operation. Okay. When I goes to 1, then we're going to go from 1 to less than or equal to n to the 1. So how many times is print going to go? N. Okay. Okay, so you see the pattern. So what's going to happen on the second one? When I goes to 2, goes from 1 to less than or equal to n to the second power. So that's going to be n squared plus 1 to get out, but this is the characteristic operation. That's going to go n squared. So it's going to go 1, n squared, n cubed, n to the 4th power, n to the 5th power, etc. Up to when I goes to n minus 1, then it's going to go from 1 to less than or equal to n to the n minus 1 power. So how do you find the complexity of that? It's pretty hard, right? So Lokesh and I were just talking about it. So I thought I'd just show you, not so much that I want you to be able to solve this, I'll tell you how to solve it because it's not that difficult. You need to be, well, I'll show you kind of what I'm doing here. So what we have is, we have essentially the summation as I goes from 0 to n minus 1 of n to the I, correct? I think that's what we have. So then you can see that the characteristic operation, which is the most simple. Now, of course, the instruction count here and here is much easier. What's the instruction count here? Just n. Yeah. It's going to be n minus 1 true and 1 false. So n, and of course, so you can get that. And of course, this one is going to be just one more than this every single time. So we have n to the 0 plus n to the 1 plus n to the 2 plus dot 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 plus n to the n minus 1. So the problem with that is that it doesn't look like anything that we've seen before. It's a little bit different, right? So, but it's a function. It's actually what it is. It's a polynomial function. So we have a constant, we have n squared, n cubed, all the way to n minus 1 power. So we have a polynomial function. So polynomial function. Now, but we have no way of summing these elements. Right? Because if you think about it, right? So how do you add all these values together? Because that's one of the constant changing. Now, if you were to graph this function, what do you think this function would look like as the value of n is increasing? So for example, if you just look at this one, this is 1. Because eventually, let's say we go from 0 to 3. So it's just going to be 0, 1, 2, 3, right? We go to 4, 0, 1, 2, 3, 4. What do you expect this function to be doing? It's getting bigger, smaller, staying the same? It's increasing. So, would you say this function is strictly increasing? Yeah, so this function is strictly increasing. So this function is going up. You can graph it yourself. You can graph it yourself. You see that basically as you add each term, it's just getting bigger and bigger and bigger. Because we assume that n is a positive number. And so what we can say is that this summation, as I goes from 0 to n minus 1 of n to the I, would be less than or equal to, now we can put an integral into here. Because sometimes an integral, some things may be easier to integrate than to try to find the discrete values. So we're going to go from, the integral has to be the same. Now the function is strictly increasing, which means that every function that's discrete and continuous matches on the integer. They're the same. But if a function is increasing, as soon as it passes the integer, it's bigger. So that means the area under that is going to be a bigger area than the rectangle from the lower limit. So therefore we can start at the lower limit of 0, And to have the same width, we have to end up where? What's our upper index going to be? No, what's our upper index going to be? No? Not n minus 1. Remember, we have to have the same width. We talked about that. We're talking about using the bounds. If you had, okay, so if you had the summation here, as I goes from 2 to 5 of some function of I. Okay, let's say it's an increasing function. So it's less than or equal to some integral of f of x dx, right? Now, since it's increasing, we can start here. Because as soon as they both hit 2, they're in the same value. And this one is increasing immediately, so it's an upper bound. But remember, 2 goes from 2 to 3. 3 goes from 3 to 4. 4 goes from 4 to 5. And 5 goes to 5 to 6. So I have to end here at 6. So I have to end here at n. That's the important thing. And so what's the integral going to look like? This is the variable. So it's going to be n to the x dx. So now, we talked about taking derivatives of e to the x, but not n to the x. What is n? N is a constant. What's e? It's a constant. So the nice thing about e is that the derivative of e to the x is e to the x, and the integral of e to the x is e to the x. But if you have something other than e to the x, let's say you have some other constant to the x, if you have an integral, it becomes a little bit different. And there's an easy way to solve it. If you're really interested, I can show you how to do it. But don't worry about it. So basically, what this is going to do is this is going to look like 1 over natural log of n times n to the x. Okay? So that's what it's going to be. And then you have to evaluate this from n down to 0. So the derivative of n to the x, when n is constant, is 1 over natural log of the base times n to the x. So it's very similar. E to the x, integral is e to the x. Well, this is still the same thing, except you have to divide it by natural log of the base. That's the adjustment factor. It's like a scalability factor. How it's done, I can show you if you're interested. And if you're not, I'm not going to test you on it, so don't worry about it. So all we need to do is now take 1 over natural log of n, and then we're going to take this part right here and evaluate it from n. So what we're going to have is we're going to have n to the x as x's value. So it's going to be n to the n minus n to the 0, which is 1. So what we have is we have 1 over natural log of n times n to the n. That is what? That is the upper bound of that function, which is a kind of cool result. Now, the question is, that, oh, okay, this is just fell asleep, right? I'm not doing anything with it. So the question is this a very tight upper bound or is it a loose upper bound? Well, that's a different story. It is an upper bound. But if you're not sure if this is tight or not tight, what could you do? As an algorithm analyst, if you wanted to find out how much off could I be, give me the whole interval of my error. What could you do? So the summation is someplace here. The integral gives you an upper bound here. What else could you get? Get the lower bound, because once you have the lower bound, then you have nailed down the minimum and the maximum that this summation is in. So it depends on how close it is. So to do that, you would need to do this. So you would have the integral from where to where? So now we need a lower bound. Lower bound is a little trickier. Because it's trickier only because the summation starts at 0. It starts at 0. So think about it. If the summation starts at 0, and it's increasing right away, then if you start at 0, you're going to be too much. So you got to start at -1. You got to back it up. So the integral has to go, we'll just put it here, from -1, what's the upper index going to be? N minus 1. And why? Same width. So if you're going to go down by 1, go down by 1, and that keeps the integral, this is the same, and that's going to be n to the x dx. Okay? Now, in some cases we have a problem because sometimes areas that are negative might give you some negative values, but I think in this case we're going to be okay. So the integral of nx dx is still going to be exactly the same. So it's going to be 1 over ln of n to the x. This time we're going to go from n minus 1 to minus 1. And you can see that this is going to be 1 over natural log of n times n to the n minus 1. And then it's going to be minus 1 over n. Minus n to the 1 over n. So that is the lower bound. And then is the upper bound. Now I can say, how far am I going to be? How often am I going to be? And the answer is very simple. I don't know. But if you have a specific value for n, I can give you the integral. For example, if I know n is equal to, for example, 10, then it's going to be 1 over log of 10, 10 to the 9th minus 1/10. Okay, that's going to be the least, and here's going to be the most, and you can calculate a specific width of the value. Okay, so that's how you can solve it. But again, I don't expect you to be able to solve it because it's not something we went over, but the technique is very close to what we did. The only problem we really had was that we didn't have the integral of n to the x. If it was e to the x, we would have been good. So if you fix it at e, then you're easy. Then it's easy. But n was not the easier one. All right. Any questions about that? So a little bit on that, and then we can leave that idea. Okay. So the next thing I wanted to do is, first of all, so master theorem. Let's talk about the master theorem. So what do you take away from the master theorem? Basically, you take away from the master theorem is that functions that go into a particular pattern, what's the pattern of functions that we can get the quick analysis of complexity? So we have T of n is equal to what? What type of complexities can we solve with master theorem? Yes, and give me a pattern. Because not all of them can be solved through master theorem. So go ahead. A times
T of n by b.
T of n over b plus
N power k.
plus forget about theta. Plus f of n. Right? So the complexity T of n is equal to A times T of n over b plus function of n. So what is f of n? What is f of n in this case? What is f of n? For example, we I think, look, let's talk about merge sort. Talk about merge sort, right? So merge sort is I want you to merge sort 1 through n. So the first thing merge sort does is says I want you to merge sort 1 through n over 2. Then it says I want you to merge sort n over 2 plus 1 to n. And then it says merge them. Right? Well, which part of it is the f of n? The merge. The merge. So you got these two halves that are kind of already, right? So you got this, so which one is it? Okay, you're merging them. So that's the comparisons and so this is called the actual complexity. So f of n n is the actual complexity. So when we talked, you guys talked about recursive level 0? I think we mentioned it in class. Recursive level 0 is the actual complexity when you're first calling the function from the outside. And then the function, like in merge sort, splits into the left side and the right side. Okay? So the actual complexity is how much work you do on that level. So in the case of merge sort, we had T of n is equal to 2T of n plus, not C, plus what?
N.
Plus n, which n was the actual complexity of merging. So, so if I'm sending an array, let's say from 1 all the way to n, into here, right? So what I'm going to do is I'm going to take that array, cut it in half twice, left branch, right branch, but then I'm going to merge it at the end. That's my cost. So the cost at level 0 is n. But now, as you saw from the recurrence tree, when you start with n, you're going to split it, and here you're going to go to n over 2, and you're going to go n over 2. So again, you're going to split those n over 2s, and you're going to get 2 n over 4s on each side, but then you're going to do the actual complexity here. So the left branch, this is level 0, this is level 1. Notice that level 1 occurs 2 times. The actual complexity at level 0 is going to be equal to n, whatever's coming in. But what's coming in is n over 2. So your actual complexity is going to be n over 2 on this side, n over 2 on this side, for a sum of n. So the two level 1s combine for an actual cost of n. One level 0, actual cost of n. How many level 2s am I going to have? 4. Actual cost of n over 4, n over 4, n over 4, n over 4, total cost of n. So actually what's going on with the actual cost on each level? The actual cost at each level stays the same. So the only question is, how many levels do you have? How many times can I cut something in half? Well, if you take 16, I can cut it to 8, 4, 2, 1, 4 times. If I take 32, I can cut it to 16, 8, 4, 2, 1, 5 times. So it looks to me like the relationship between cutting something in half is exactly log base 2. So that's why the cost of this function, in this case merge sort, will be log n, which is the number of times you can cut something in half, times n, which is the cost of doing all the levels. Each of them is a cost of n, as you saw, and we have log n of them. So n log n is the analytical result. Okay, so going back to this, so we had T of n is equal to A times T of n over B plus F. So this is actual complexity. So for example, the actual complexity in merge sort was F of n was equal to actually n. But in some cases, the actual complexity could be n log n, or it could be n squared, or it could be the square root of n, or it could be log n, right? The actual complexity is whatever it is. That's why we say function of n. Some function. And if this is the actual complexity, then what do you think we're going to call this? I'm sure the kids didn't play that, but that's okay. What do you think this is going to be? If this is the actual complexity, what is this? Or sometimes I use a different word. I say actual cost. Actual cost, right? So this is the what kind of cost? Recurrent cost. Or recursive cost. So you can think of this as a recursive cost. And you can also think of this as the actual cost. Okay? So in the master theorem, we compare f of n against what other quantity? N to the log base no, well, not in this example, in general. Log base 1 of what? You did go over the notes, right, in the class? Did you see this? n to the log base b of a, right? Does that ring a bell? Does that sound familiar? Yes or no? You've seen it, right? Okay, so, now, what is this? What is f of n? If you had to tell me f of n exactly, it's the cost of level 0. Actually, that's what it is. F of n is the cost of level 0. Now, do we understand what n to the log b of a is? Does anybody, did you get to that part, Lokesh? Did you explain what n to the log b of a is, this magical quantity?
No.
All right, well, we're gonna get to it. So watch very carefully. Watch very carefully. We learned in our mathematical discussions earlier in the semester that n to the log b of a is equal to a to the log b of n. You remember that? When we talked about logs. That was one of those cool results that everybody said, wow, this is cool, so what? Well, actually, it's very interesting. Because if you look at the master theorem, what does the A represent in terms of the recursion tree? What does the A represent in terms of the recursion tree? If we have the first level, level 0, what does A demonstrate? For example, go ahead. More specifically. For example, I could have, for example, let's see, T of n is equal to 3P of n over 4 plus f of n. I could have another one, T of n is equal to 4 times T of n over 2 plus f of n. Hello? Okay? So what I'm saying to you is that there are different values of A I could have, right? Okay, so look at this one, which is some function. Look at this one, it's another function. And look at, we don't have, well, you know what we had before, we had merged sort, right? Which was what? 2t of n over 2 plus f of n. Where f of n is n. Okay, so the question is, what does this A coefficient represent in front of the t?
The number of
recurrences?
Yes. Okay, and from a tree perspective, what's the better vocabulary? Number of? Number of branches. Okay, that's, I know you're there. I just want to, can we just agree on some wording here? So this A coefficient is the number of branches. So if I'm going to draw this tree right here, I don't know why I'm using this overhead, because I'm not using it at all. But now I can use the whole board. But if I'm going to draw this one right here, I would show this. N would come in here, and so therefore what I would have is f of n would be, as n comes in here, I perform f of n at level 0. Level 0. Then I split how many times? 3 times. 3 times. And for each of them, I'm sending in what part of the problem? N over 4. So it's going to be f of n over 4. Get it? F of n over 4, and then f of n over 4. Right? And as I go again, that's level 1. The sum cost of level 1 is going to be the sum cost of all these level 1s. The sum cost of level 0 is f of n. So now, from each level 1, I generate how many level 2s? 3 again. 1, 2, 3, 1, 2, 3, 1, 2, 3. And of course, each time I send in a quarter of what I had. So now I have what? F of a quarter of n over 4, which is n over 16. 3 times, right? And the same thing here, and the same thing here, and the same thing here. So that's what's going on. Now if I go to this one, I start with f of n on top. I split into how many branches? 4 branches. Each one takes half, so therefore it does f of n over 2. But it does it 4 times at level 1. And then from these 4 branches, each of them generates 4 branches, which takes half of that. So it's going to be f of n over 4, 4 times, f of n over 4, 4 times. There are going to be 16 of them. 16 times n over 4. You get the idea, right? Okay, so Let's go back to here. Can you see this? You can see it?
Yeah.
Okay, so so let's go back to here. So we understand that these two things are being compared against each other. We're trying to figure out which one is bigger, actually. Because in the two cases where one is bigger than the other, then we say, okay, then the algorithm is theta, the bigger one. And in the case of this is bigger, okay, the algorithm is theta of that one. Remember that? That was case 1 and 3. Case 2 was where they were doing what? They were the same. It had that really weird K in there. But basically they were the same. So the idea here is, so we're comparing them. But the question is, what exactly are we comparing? Well, I know for sure that this is the cost of level 0. So there's going to be one computational node doing f of n operations. But when does recursion stop? When the leaves get an input of size 1. So therefore, in order to find out how much work is being done at the bottom level, all I need to do is not count how much work this node is doing. I know the leaf node is doing a unit of work. So what I'm interested in is, how many do I have? Well, interestingly enough, n to the log b of a, which is kind of a polynomial type expression, is equivalent by logs a to the log b of n. But log b of n is what? What does this represent? What is log b of n? That represents the number of times you can take n and divide it into b equal parts. Log 2 of n is how many times can you cut n in half. Log 3 of n is how many times can you cut n in 3 parts. So if n is 27, you cut it in thirds, you get 9s. You get 3s, you get 1s. That's log 3. Log 2, you have 32, you have 16, 8, 4, 2, 1, eventually you get unity. So log b of n is the number of times that I can cut n into b parts in order to achieve unity. Okay, so now tell me in a better, smarter way, what exactly does log b of n represent in the tree? The height of the tree. Got it? The height of the tree. It's the height of the tree. So now, since this is the height of the tree, what does this represent? It represents the number of branches. So if the height of the tree is 1, look at this, if the height of the tree is 1, then a to the 1 is the number of branches we have. Well, like, for example, let's say a is 4, like in this example. Well, let's say 3. If a is 3, how many branches do we have here? 3. But if the height of the tree is 1, it's 3 to the 1. But if the height of the tree is 2, and a is 3, then we actually going to have 9. So actually, a to the log b of n is exactly the number of nodes at the leaf level. Each of them doing how much work? Unity work. So therefore, the total work being done at the leaf level is a to the log b of n, which happens to be equal to n to the log b of a. So, if we know that the work is increasing exponentially, then the amount of work being done at the leaf level is proportional to the theta complexity of everything. If the amount of work is decreasing exponentially, then the amount of work being done at level 0 is theta proportional to all the work being done. Do you know why? Well, it's not that complicated, because you guys know the powers of 2. Imagine that this tree basically is doubling. So that means a is equal to what? It's doubling, so a is equal to what? 2. So we're going to get here, right? So let's find out. We have 2 to the 0, 2 to the 1, 2 to the 2, and finally 2, let's say 2 to the, 2 to the n minus 1. Look over here. So how much work is being done at the bottom level? Exactly 2 to the n minus 1 work, because each of them is doing unity work at the leaf level. So why is the amount of work being done here theta of the whole tree? That's because what we have is 2 to the n minus 1, and we know that the rest of this tree has what amount? 2 to the n minus 1 minus 1. When you add them together, you will get the total work in the tree, which is equal to what? 2 to the n minus 1. So basically, when the base is 2, the bottom does approximately 50% of the work. That means everything else is about 50%, so that means the bottom is theta of everything. Okay, if A is equal to 3, it's a different ratio, but it's still proportional, because what we have here, if we have 3, then we start having something like this. We have 1, and then we're going to go to 3, right? So it's going to be, and then we're going to go to 3 times 3, which is going to be 9. So we have 3 to the 0, 3 to the 1, 3 to the 2, and ultimately 3 to the n minus 1. Okay? So, what we have to find out is what is the sum of the values of summation from 3 to the 0 to 3 to the n minus 2. And when you find the answer to that, this is going to be through the I, you're going to find out that this is all proportional, because what is this? This is a geometric series, isn't it? 0 to n minus 2, geometric series. What's the first term? 1. What's the second term? 3. What's the, okay. What's the last term? 3 to the n minus 2. Okay. So now we know this, the solution for the geometric series is going to be a minus ar to the n over 1 minus r. A is the first term, minus a times r, 3 to the number of terms. This is 3 to the 0, so I think it's going to be n minus 1.
Yeah.
So it's going to be n minus 1 divided by 1 minus r. So now multiplying top and bottom by negative 1, we get 3 to the n minus 1 minus 1 over 2. Over 2. So that is the amount of work being done up to the very last level. So the question is, what proportion is it? Well, what you can do is you can take this number 3 to the n minus 1 and divide it by the sum of these two, which would be 3 to the n minus 1 plus 3 to the n minus 1 over 2. Am I right? No? 3 to the n minus 1 minus 1, right?
Yeah.
Okay. So that's going to be 3 to the n minus 1 over, this is going to be, this is to put over 2, this is going to be 2 times 3 to the n